Series circuits are utilized to limit current flow and to protect components from overcurrent situations. Fuses and circuit breakers exemplify this. Consider simple resistive lighting circuits, such as a string of Christmas lights wired in series. Another application involves dimming lights using variable resistors, like rheostats, which are connected in series with the light. In a series circuit, the current is the same through each component while the voltage is divided among them. If one component fails, the entire circuit is broken. An example of a series circuit application is a series of outlets connected in a single loop, like a room circuit. Also, electrical fuses serve as a safety device in series, breaking the electrical connection when excessive current flows. Parallel circuits, conversely, provide multiple paths for current flow, thereby increasing the total current capacity. These are commonly found in electrical distribution systems, branching power to different areas, such as house outlets and industrial machinery. Lighting systems often use parallel circuits to allow individual lights to be turned on and off independently. Car audio systems employ parallel circuits to connect multiple speakers to a single amplifier. In a parallel circuit, the voltage is the same across each branch, while the current divides among them. If one branch fails, the other branches continue to function. A home electrical system with multiple circuits running in parallel to distribute power throughout the house is a prime example. Similarly, car battery connections feature multiple terminals connected to the battery to allow for multiple loads, such as headlights and a radio. Series/parallel circuits combine elements of both series and parallel configurations. They offer flexibility in current flow and voltage distribution. Electronic devices use series/parallel circuits to create complex circuit functions. Common applications include power supplies, amplifiers, and filters. These circuits balance the characteristics of series and parallel circuits to achieve desired performance. An example is a transformer, a device that uses series and parallel windings to change voltage and current levels. Another application is an electronic power supply, a circuit that converts AC to DC power, often using a combination of series and parallel elements. Let's delve deeper into series circuits. The defining characteristic of a series circuit is that the current has only one path to flow. This means that the same amount of current flows through each component in the circuit. A simple analogy is a single-lane road. All the cars must travel the same path. If there's a blockage anywhere on the road, traffic stops for everyone. In an electrical circuit, that blockage would be an open circuit or a component failure. The total resistance in a series circuit is simply the sum of all the individual resistances. For example, if you have 3 resistors of 10 ohms, 20 ohms, and 30 ohms connected in series, the total resistance is 10 ohms plus 20 ohms plus 30 ohms, which equals 60 ohms. The voltage supplied to the series circuit is divided across each of the resistors proportionally to their resistance. Using Ohm's law, which states that voltage equals current times resistance, you can calculate the voltage drop across each resistor. If a 12 volts battery is connected to the previous series circuit, the current would be 12 volts divided by 60 ohms, which equals 0.2 amps. Then the voltage drop across the 10 ohms resistor would be 0.2 amps times 10 ohms, equaling 2 volts. Similarly, the voltage drop across the 20 ohms resistor would be 0.2 amps times 20 ohms, equaling 4 volts, and the voltage drop across the 30 ohms resistor would be 0.2 amps times 30 ohms, equaling 6 volts. Note that the sum of the voltage drops, 2 volts plus 4 volts plus 6 volts, equals the total voltage of 12 volts. The primary application of a series circuit is to limit the current. A fuse is a perfect example. It's a thin wire designed to melt and break the circuit if the current exceeds a certain level, protecting more expensive components from damage. Another application is a voltage divider, where you need to obtain a specific voltage from a high voltage source. You can use a series of resistors with appropriate values to achieve the desired voltage at a particular point in the circuit. Think of older Christmas tree lights. When one bulb failed, the entire string went out because the bulbs were wired in series. This illustrated one of the main disadvantages of series circuits. However, modern Christmas lights use parallel or series/parallel arrangements to avoid this problem. Now let's consider parallel circuits. In a parallel circuit, the voltage is the same across all components. However, the current divides among the different branches based on the resistance of each branch. Think of a multi-lane highway. Each car can choose its own lane, representing a different path for the current to flow. If one lane is blocked, the other lanes remain open and traffic can still flow. The total resistance in a parallel circuit is calculated differently than in a series circuit. The reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. The formula is 1 divided by R total equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 and so on. If you have 3 resistors of 10 ohms, 20 ohms, and 30 ohms connected in parallel, the total resistance is calculated as follows: 1 divided by R total equals 1 divided by 10 ohms plus 1 divided by 20 ohms plus 1 divided by 30 ohms. This simplifies to 1 divided by R total equals 0.1 plus 0.5 plus 0.333, which equals 0.1833. Therefore, R total equals 1 divided by 0.1833, which is approximately 5.45 ohms. Since the voltage is the same across all the resistors in a parallel circuit, you can use Ohm's law to calculate the current through each resistor. For example, if a 12 volts battery is connected to the previous parallel circuit, the current through the 10 ohms resistor would be 12 volts divided by 10 ohms, which equals 1.2 amps. The current through the 20 ohms resistor would be 12 volts divided by 20 ohms, which equals 0.6 amps. The current through the 30 ohms resistor would be 12 volts divided by 30 ohms, which equals 0.4 amps. The total current drawn from the battery would be the sum of the currents through each resistor, 1.2 amps plus 0.6 amps plus 0.4 amps, which equals 2.2 amps. Parallel circuits are used whenever you need to provide the same voltage to multiple devices independently. Home wiring is a classic example. All the outlets in your house are wired in parallel. This means that each outlet receives the same voltage, typically 120 volts in North America, and each device plugged into an outlet can draw the current it needs without affecting the voltage to other devices. If one device fails or is turned off, the other devices continue to operate normally. Car audio systems also use parallel circuits to connect multiple speakers to an amplifier. This allows each speaker to receive the same audio signal and produce sound independently. Finally, let's discuss series/parallel circuits. These circuits combine both series and parallel elements to achieve more complex functionality. In a series/parallel circuit, some components are connected in series, while others are connected in parallel. This allows for both voltage division and current division, providing greater flexibility in circuit design. The analysis of series/parallel circuits involves breaking down the circuit into simpler series and parallel sections. You can then calculate the equivalent resistance of each section and combine them to find the total resistance of the circuit. Power supplies are a common example of series/parallel circuits. Power supplies convert AC voltage from the wall outlet to DC voltage that electronic devices can use. They often use a transformer to step down the voltage, followed by a rectifier circuit to convert AC to DC, and then a filter circuit to smooth out the DC voltage. The transformer typically uses series/parallel windings to achieve the desired voltage transformation ratio. The filter circuit may also use series and parallel combinations of capacitors and inductors to reduce the ripple voltage. Amplifiers also utilize series/parallel circuits. Amplifiers increase the amplitude of an input signal. They often use transistors or vacuum tubes as active devices. The biasing circuitry for these active devices typically involves series and parallel resistors to set the operating point of the device. The amplifier may also use feedback networks, which can involve series and parallel components to control the gain and stability of the amplifier. Filters are another example of series/parallel circuits. Filters are used to selectively pass or block certain frequencies. They can be designed using combinations of resistors, capacitors, and inductors. A simple RC filter consisting of a resistor and a capacitor can be connected in series or parallel to create a low-pass or high-pass filter. More complex filters, such as band-pass or band-stop filters, may use multiple stages of series and parallel RC or RL circuits. Understanding series, parallel, and series/parallel circuits is fundamental to electronics. These circuits are used in a wide variety of applications, from simple lighting circuits to complex electronic devices. By mastering the principles of these circuits, you can gain a deeper understanding of how electronics work and be able to design and troubleshoot your own circuits. Understanding series and parallel circuits also help with understanding complex combinations. By reducing the combinations down using the series and parallel rules, it makes the circuit understandable, one portion at a time. Consider the following example. Imagine a circuit consisting of a 12 volts battery connected to a series combination of two resistors. Resistor 1 has a resistance of 10 ohms, and resistor 2 has a resistance of 20 ohms. Now a third resistor, resistor 3, with a resistance of 30 ohms, is connected in parallel with resistor 2. To analyze this series/parallel circuit, we first need to find the equivalent resistance of the parallel combination of resistor 2 and resistor 3. The formula for the equivalent resistance of two resistors in parallel is R equivalent equals R2 times R3 divided by R2 plus R3. Plugging in the values, we get R equivalent equals 20 ohms times 30 ohms divided by 20 ohms plus 30 ohms, which equals 600 ohms squared divided by 50 ohms, which equals 12 ohms. Now we have a series circuit consisting of resistor 1, with a resistance of 10 ohms, and the equivalent resistance of the parallel combination, which is 12 ohms. The total resistance of the circuit is simply the sum of these two resistances, which is 10 ohms plus 12 ohms, which equals 22 ohms. The current flowing through the circuit can be calculated using Ohm's law. Voltage equals current times resistance. Current equals voltage divided by resistance. Current equals 12 volts divided by 22 ohms, which equals approximately 0.545 amps. Since the current is the same through all components in a series circuit, the current through resistor 1 is also 0.545 amps. The voltage drop across resistor 1 can be calculated using Ohm's law. Voltage equals current times resistance. Voltage equals 0.545 amps times 10 ohms, which equals 5.45 volts. The voltage drop across the parallel combination of resistor 2 and resistor 3 is equal to the total voltage of the battery minus the voltage drop across resistor 1, which is 12 volts minus 5.45 volts, which equals 6.55 volts. Since the voltage is the same across all components in a parallel circuit, the voltage across resistor 2 and resistor 3 is also 6.55 volts. The current through resistor 2 can be calculated using Ohm's law. Voltage equals current times resistance. Current equals voltage divided by resistance. Current equals 6.55 volts divided by 20 ohms, which equals approximately 0.328 amps. The current through resistor 3 can be calculated using Ohm's law. Voltage equals current times resistance. Current equals voltage divided by resistance. Current equals 6.55 volts divided by 30 ohms, which equals approximately 0.218 amps. Notice that the sum of the currents through resistor 2 and resistor 3 equals the total current flowing into the parallel combination, which is 0.328 amps plus 0.218 amps, which equals approximately 0.546 amps. This confirms our calculations. By breaking down the series/parallel circuit into simpler series and parallel sections, we can analyze the circuit and determine the voltage and current for each component. The NEC National Electrical Code provides guidelines for safe wiring practices. Article 310.15 covers ampacity, the current carrying capacity of conductors. Table 310.16, for example, specifies the allowable ampacities for insulated conductors rated up to 600 volts, not more than 3 conductors in a raceway or cable or earth, based on ambient temperature. This table is crucial for selecting the correct wire size for a given application to prevent overheating and fire hazards. For example, if you have a 15 amp circuit, you would typically use 14 American wire gauge copper wire, according to table 310.16. However, the specific wire size may vary depending on the type of insulation, the ambient temperature, and other factors. Always consult the NEC and local codes for the most accurate and up-to-date information. Remember that electrical work can be dangerous and should only be performed by qualified individuals. The NEC also addresses overcurrent protection in Article 240. This article specifies the requirements for fuses and circuit breakers, which are designed to protect circuits from overloads and short circuits. The size of the overcurrent protection device must be matched to the ampacity of the conductors it is protecting. For example, a 15 amp circuit should typically be protected by a 15 amp circuit breaker or fuse. Using an oversized overcurrent protection device can allow excessive current to flow, potentially causing damage to the wiring and equipment. Grounding is another important aspect of electrical safety, covered in Article 250 of the NEC. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and energize the circuit. This helps to prevent electrical shock hazards. The NEC specifies the requirements for grounding electrodes, grounding conductors, and equipment grounding conductors. Proper grounding is essential for the safe operation of electrical systems. In addition to the NEC, there are other standards and regulations that may apply to electrical work, such as those issued by UL, Underwriters Laboratories, and ANSI, American National Standards Institute. It is important to be familiar with all applicable standards and regulations before performing any electrical work. Different types of cables exist, like non-metallic sheath cable, often referred to as NM cable, is commonly used for residential wiring. It consists of 2 or more insulated conductors enclosed in a non-metallic sheath. NM cable is typically used for branch circuits and feeders in dry locations. Armored cable, often referred to as AC cable, consists of insulated conductors enclosed in a flexible metal armor. AC cable is used in both dry and damp locations and provides additional protection against physical damage. Metallic conduit, such as rigid metal conduit and electrical metallic tubing, is used to protect conductors in exposed locations or where there is a risk of physical damage. Conductors are installed inside the conduit. Understanding these common wiring methods and cable types is essential for electrical work. Electrical boxes are used to house electrical connections, such as splices and terminations. They provide protection for the connections and prevent them from being exposed to the environment. The NEC specifies the requirements for electrical boxes, including the size, material, and installation. Electrical boxes are typically made of metal or plastic and come in a variety of shapes and sizes. When sizing an electrical box, you need to consider the number and size of the conductors and devices that will be installed in the box. The NEC provides guidelines for calculating the minimum box size required. Receptacles, also known as outlets, provide a point of connection for electrical devices. They are typically installed in walls or floors and come in a variety of configurations, such as duplex receptacles, DFCI receptacles, and USB receptacles. The NEC specifies the requirements for receptacles, including their location, mounting height, and grounding. GFCI ground fault circuit interrupter receptacles are required in wet locations, such as bathrooms and kitchens, to protect against electrical shock hazards. Switches are used to control the flow of electricity to lights and other devices. They come in a variety of types, such as single-pole switches, three-way switches, and dimmer switches. The NEC specifies the requirements for switches, including their location, mounting height, and wiring. Three-way switches allow you to control a light from 2 different locations. Dimmer switches allow you to adjust the brightness of a light. Lighting fixtures provide illumination for homes, businesses, and other spaces. They come in a wide variety of styles and types, such as incandescent lights, fluorescent lights, and LED lights. The NEC specifies the requirements for lighting fixtures, including their location, mounting height, and wiring. LED lights are becoming increasingly popular due to their energy efficiency and long life. Branch circuits are the circuits that extend from the main service panel to the various outlets, lights, and appliances in a building. The NEC specifies the requirements for branch circuits, including their size, number of outlets, and overcurrent protection. Branch circuits are typically rated at 15 amps or 20 amps. Feeders are the circuits that carry power from the main service panel to sub-panels or other distribution points. The NEC specifies the requirements for feeders, including their size, ampacity, and overcurrent protection. The size of the feeder must be sufficient to carry the load it is supplying. Service panels are the main distribution points for electricity in a building. They contain the main circuit breaker, which disconnects all power to the building, as well as the branch circuit breakers and feeder breakers. The NEC specifies the requirements for service panels, including their location, size, and grounding. Service panels must be accessible and properly grounded. When working with electrical systems, it is important to follow all safety precautions. Always turn off the power to the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. Never work on electrical systems when you are wet or standing in water. If you are not comfortable working with electricity, hire a qualified electrician.